All right, we're going to begin chapter 1, section 5, where we discuss complex and imaginary numbers. All right, so I first want to start with what an imaginary number is. Right, so maybe you've heard of it before, maybe you haven't. Maybe if you haven't, it sounds kind of ridiculous that we're even talking about something like this in math. All right, but what an imaginary number essentially is it's used to handle the square root of any negative number, right? So let's say I had the square root of negative 20, right? Something like that, we don't really know where it's going to fit on a number line. And think about the number line that you learned since like elementary school, right? Maybe when you learned how to count, we started with 1, 2, 3, 4, and so on, all right? And then maybe later on you learned about fractions, right? Something like a half is maybe less than 1, right? So maybe something right there. Maybe like 5/4 would be right there. Negative numbers, right? So we learned about 0 and the negative numbers, so -1 and so on. And then even things like radical 5, right? So square root of 5, right? All of these, basically any number that you could think of can fit on a number line, right? Pi, right, that you learned in geometry, right? Pi, little above 3, right? But if I take something like the square root of -20, that really has no place in this number line, all right? So we kind of have to create a whole new number system, or not create, but there was like a whole number system that was developed and expanded to kind of extend our knowledge of what numbers could possibly be, right? So something like the square root of 20 and the square root of -20 and the square root of -30, even though they're both what you guys would maybe consider now like no solution, right? We discussed that before. It's something that maybe you can tell that even though they're technically, I guess, no solution in the real number system, they're obviously not the same number, right? The square root of -20 and the square root of -30 are not the same thing. All right, so we can use imaginary numbers to kind of put a name to what would otherwise be a no solution or something that we can't handle. All right, so something to note is that the square root of -1 is what we represent with the letter I, right, which is what we call the imaginary unit. All right, and it represents the square root of -1. So then something else that you might see is I squared is equal to -1, right? So square both sides of this equation, and then you get I squared is -1. And so again, like I said, we use it to handle the square root of any negative numbers, and they do exist, right? So when I say they are real, I just mean that they exist, right? So it's not like, I know the name imaginary is a little bit of a misnomer, right? So they exist, right? Because we're working with them, right? Anytime you get a square root of a negative. And then you'll see the connection to this and what we did in the past, like with solving quadratic equations. For example, if I give you something like x squared equals 4, right? We know that we can square root both sides and I get x equals plus minus 2. But something like x squared equals -4, we're going to eventually have to take the square root of a negative, which after this lesson, we'll know what the answer of this is supposed to be, right? So just keep something like this in the back of your head. All right, so we're going to start this lesson on imaginary numbers with simplifying negatives under a radical. All right, so kind of the essence of what we're trying to do here is to simplify radical answers, right? So anytime you see a negative under the radical, we can remove the negative by extracting the I, so taking the imaginary unit out, and then you simplify whatever's remaining as normal. And you can write your answers as maybe you have a real number with an I. If you have a radical, right, I can have the square root of that number after the I, just because, like, let's say I had the square root of 3i. I don't want to make a mistake and accidentally extend that square root out and have that I underneath the radical, right? That would not be correct. So just to avoid that confusion, we can put the I in front of the radical. Or maybe you have a whole number and a radical with an I. You can put the I in between. So something like 2 square root of 5 with an I, right? I don't really want to put the I right in front, right? Nor do I want to put it in the back, right? We can put it right in the middle, all right? So some examples, something like the square root of negative 16. I see a negative underneath the radical, so I can take out the I and then leave everything else underneath. And then see if we can simplify that, right? The square root of 16 is 4. So then the square root of negative 16 gets us 4i. All right, and I can do the same thing with something like square root of negative 20. All right, again, I see a negative underneath the radical. You can take that out as an I. And then you would simplify the square root of 20, same thing as before, right? 4 and 5, 2 and 2. And so I get 2 the square root of 5, and then like I said, I would put the I right in between. All right, so looking at this square root of negative 3, like we said in the previous slide, I can take that negative underneath the radical and immediately convert that to an I. And then I can leave whatever's left over underneath the radical. Now in this case, radical 3 cannot simplify any further, so our answer would just be I square root of 3. All right, but looking at the next one, square root of negative 48, once again, I can take that negative and convert that to an I, and then leave whatever's whatever's left over underneath the radical. This one we can break up though, right? 48 can be broken up into 16 and 3. All right, and the square root of 16 is 4. And the square root of 3 doesn't break down anymore, so I get 4 square root of 3 and an I. Like we said in the previous slide, I can write this as 4i square root of 3. Now, the reason we would write it like this as opposed to another way, maybe something like 4 square root of 3i, like I said in the previous slide, right? You don't want to extend that square root and then have it look like that, right? If I see that on a test or a quiz, I would mark that wrong. All right, and then also maybe something like I4 square root 3 looks a little awkward, right? So find a good sweet spot, right? Something like that. So again, both of those, yeah, don't worry about those. Right? Just write it like this. All right. Now, when you multiply two numbers that have a negative under the radical, what we can start off with is first getting rid of the negative by taking out the I. Right. So I see a negative 7, that's going to become an I square root of 7, right, times, and then this same thing over here, this negative is going to become an I square root of 7. All right, and then you can go ahead and multiply these, right? I can do I times I, which is I squared, and then I can do the square root of 7 times the square root of 7, which is the square root of 49, which is just 7. All right, but refer to the previous slide, right? I squared has a value, right? We're not just going to leave it like this. Right, I squared is the same as negative 1, right? So this is negative 1 times 7, which is negative 7. All right, so always simplify your I squareds, right? They're always going to give you a negative 1. Right, same exact thing for this next one. Right, again, any negatives underneath the radical, you can immediately take out that I. So this is going to become I square root of 6 times this negative is going to become an I square root of 10. And then again, I times I is going to get you an I squared. And then square root of 6 and square root of 10 is the square root of 60, right, which we can simplify. All right, so you can split this up into 4 and 15. And the square root of 4 is 2. 15 you can't really simplify any further. And then this is going to get you 2 square root of 15. Keep in mind this I squared is going to become a negative 1. So this is negative 1 times 2 square root of 15, which is just negative 2 square root of 15. All right, and that's a fully simplified answer. All right, if we can do it with multiplication, we can do it with division. All right, so this next one, I can take out the negative from this negative 48 and turn that into an I. So this is become an I square root of 48 over square root of 24. Right, there's nothing I have to do to that one. That one looks like a normal radical. All right, and if I can multiply underneath the radical, then I can divide underneath the radical. So this is the same as I square root of 48 over 24, right? And then 24 goes into 48 2 times. So this is the same as I square root of 2. All right, same exact thing with this next one, right? These two negatives underneath the radical, I can take those out, right? So this is going to become I square root of 70 over, on the bottom I can take out that negative and I'm going to make it I square root of 7. And then I divided by I, these are going to cancel out, right? So nothing special happens there, right? Same thing on the top and the bottom, you can cancel it out. And then we're just left with the square root of 70 over the square root of 7. And then again, I can divide underneath the radical, and I get the square root of 70 over 7, which is the square root of 10. All right, no more i's. Right, so sometimes an I shows up in your final answer, sometimes it doesn't, right? But we need to fully simplify, right? So you see that our answers don't look like anything outrageous, right? It's nothing super crazy, right? We just need to make sure that we can fully simplify these to get a final answer. All right, so now something interesting about I is that higher powers of I kind of follow a certain pattern. Right, so I'm going to start with I to the 0, right? I to the first, I know that this is just regular I, but keep in mind anything to the 0 power, no matter what the base is going to be 1, all right? Except for a base of 0, right? 0 to the power of 0 is kind of strange. We tend to avoid that, right? But I to the power of 0, right, that's just 1, right? And then I squared, we said that this is negative 1, right? That was by definition, right? If I is the square root of negative 1, right, when you square both sides, then you get that I squared is negative 1, right? Just a little side note. So then what about I to the third power, right? Surely we can evaluate this, right? Well, keep in mind, we can use our properties of exponents, and I can say that I to the third power is the same as I squared times I to the first, right? Right, because hopefully we remember from way back that if we multiply two things with the same base, then we can add the exponents, all right? But we already know that I squared is negative 1 times, and I know that I to the first is just I, right? So this is just negative I. So that means I to the third is negative I, all right? So we simplified it, got rid of that exponent, made it into something a little simpler, all right? And then let's try the exact same thing with I to the fourth, right? Well, if we don't know what this is, well, let's use a property of exponent, right? Let's change this into I squared times I squared. And this is the same as negative 1 times negative 1. And then two negatives multiplied make a positive, so this becomes a positive 1. All right, so then I to the fourth is just regular positive 1. And then I to the fifth, we can try this exact same thing. Well, I know what I to the fourth is, and I know that I to the fifth is the same as I to the fourth times I to the first, which is just 1 times I, so I get that I to the fifth is I, right? So hopefully we can see, right, this I to the 0 is the same as I to the fourth, I to the first was the same as I to the fifth, and so on, right? We can hopefully imagine that I to the sixth is going to be negative 1, right? And if you're not sure and you want to be confident, I can turn this into I to the fourth times I squared, which is 1 times negative 1, which is negative 1, right? So that does check out. Right? And I can do the exact same thing with the one right above it. Right below it. Right? This is the same as I to the 6 times I to the first, which is negative 1 times I. So negative I. Right? And hopefully you notice that these are going to keep cycling, right? So then I can say I to the 8th is 1, I to the 9th is I to the 10th is negative 1, and I to the 11th is negative I, right? So these are going to keep repeating, and I can do the exact same thing for I to the 12th, which is going to be 1, I to the 13th, which is I to the 14th, which is negative 1, right? And so on. And you can do this forever and ever and ever. All right, so there's a pattern here, right? The powers of I, they kind of cycle between every 4 powers, right? They kind of cycle between these 4 different values, right? 1, I, negative 1, negative I, all right? Now, to evaluate higher powers of I, right, what I prefer is I like to divide the exponent by 4, and then the remainder is your new exponent, and you would evaluate that, right? Another thing that you could do is you can use your properties of exponents, just like we did in the previous slide, to rewrite the expression into known values and then simplify. And I'll show you what that means in the next slide. All right, so something like I to the 32. All right, I to the 32, using I'll do the first method, right? So I'll do long division. So I'm going to show you what this would look like, and I'm going to divide by 4, right? If you notice, every 4 exponents, the cycle repeated. So I can divide 32 by 4, and then we know that 4 goes into 32 8 times. I don't really care about this number, I just care about the remainder, right? And 32 minus 32 is 0. So I get a remainder of 0. This is really what I care about. I don't care how many times it goes in. So then I get that I to the 32 is the same as I to the 0, but anything to the 0 power is 1. All right, so then I get I to the 32 is just 1. All right, doing it the other method, all right, I'll do that off to the side, is we already know that I squared is negative 1, right? And if I take negative 1 raised to any exponent, if it's raised to an even exponent, it's just going to get you a positive 1, right? If I multiply a negative by itself an even number of times, it's going to get you a positive. But if I have negative 1 to an odd exponent, this is going to get you negative 1, right? Take, for example, negative 1 to the third power. That's negative 1 times negative 1, which is 1, times negative 1 again, which is negative 1. So you go back to a negative, right? So I can change I to the 32 to be an exponent of 2 to the power of something else, right? So remember, another property of exponent is a power to a power. You multiply the powers. So I'm trying to think, what can I multiply by 2 to get 32 in my exponent, right? And that's 16, right? And if you're not sure, just divide. 32 divided by 2 is 16, right? So I get I to the 32 is I squared to the 16th, right? Because power to a power you can multiply. But I know that I squared is negative 1, and I have negative 1 to the 16th. And again, negative 1 to an even exponent we said is 1. So then this is just going to simplify to positive 1. Either way, we get the exact same answer. I prefer doing it the long division way, right? So this method up here. I feel like it's maybe a little bit quicker, but you can use whatever makes the most sense to you, right? So let's try the same thing with number 8. So I'm going to do my long division method. So I'm going to do 33 divided by 4. And I know 4 is going to go into 33 8 times, but when I do my long division, I get 1 as a remainder. So my remainder is 1. Again, I don't care about that 8, I just care about the remainder. So I to the 33 is going to be the same as I to the first, but I to the first is just I. All right? Hopefully pretty simple. Hopefully we're seeing the idea. And then I can do the same thing with 51, right? So I can do long division. I'm going to do 51 divided by 4. Looks like 4 goes into 5 one time. And then I'm going to bring down that 1. 4 goes into 11 2 times. All right, and then 4 times 2 is 8. And then so we get a remainder of 3. Again, I don't care about this 12 up top. I only care about the remainder. So I get I to the 51 is I to the third. But I to the third, as we saw from the previous slide, is negative I. Right, so there's only 4 things that you need to remember. Right, it's I to the 0, I to the first, I to the second, I to the third. Right, or maybe I to the first all the way up to I to the fourth, right, depending on how you look at it. All right. So we can try the same thing with this one. The only difference with this one is that I have a negative exponent, right? And a negative exponent I can move to the bottom. So it's going to be 1 over I to the 15th, right? And then from here I can do the exact same process, right? I can do 15 divided by 4, right? 4 goes into 15 3 times. I get 12, and then I get a remainder of 3. Again, I don't care about the quotients, I just care about the remainder. So this is the same as 1 over I to the third. And then I to the third is negative I, so I get 1 over negative I. Keep in mind, though, I is the same as the square root of negative 1, right? And the square root of negative 1 is a radical, and I don't want radicals in the bottom. So to get rid of that radical in the bottom, I'm going to multiply by I on the top and on the bottom just to rationalize that denominator, right? Make it a whole number, all right? And that's going to, let me write that down here. Right, and this is going to get us on top 1 times I, which is I, and on the bottom negative I times I, which is negative I squared, all right, but I squared is negative 1, so I get I on top, negative 1, and negative 1 is just 1, so I get I over 1, which is just I. All right, we can do the exact same thing with the next one. Any negative exponent I can move to the bottom. And then so this is going to turn into I to the 6th, or 1 over I to the 6th. And I can do the same thing, right? Long division, right? I get a remainder of 2, which is I squared. So I get 1 over I squared, but I squared is negative 1. So I get 1 over negative 1, which is just negative 1. There's no more i's. I don't have to simplify that any further. I just get negative 1 as my answer. All right. And then the next one, I to the 17th times I to the negative 13. When you're multiplying with the same base, you can add the exponents. So this is going to get you 17 plus negative 13, which is I to the 4th. And I to the 4th, as we saw on the previous slide, is 1, right? This is the one that you have to remember, right? If you didn't remember that, you could, of course, do your long division. I feel like that's a little too much work for something so simple, right? We get a remainder of 0. So we get I to the 0, which is, 1, right? So either way, we get the same answer. All right, and that's essentially how you would simplify higher powers of I. All right. Now, working with just pure imaginary numbers, right? That's everything that we've done so far, right? Just working with negatives under the radical and simplifying higher powers of I, right? Those are just imaginary numbers. The next part of this lesson is going to be complex numbers. Now, complex is any number that can be expressed as the sum of a real and an imaginary, right? So complex, right? If you think about what complex means, it just means like, maybe a little bit more complicated, right? Or things that combine other ideas, right? When you're using it in everyday language, all right? So a complex number is one that combines real and imaginary numbers, all right? And you would always write complex numbers in standard form. Standard form of a complex number is a plus bi, where a is the real part and bi is the imaginary part. For example, 5 plus 2i is an imaginary number a complex number in standard form, right? I have a real, and then I have an imaginary part. However, something like 2i plus 5, this is a complex number, but it's not in standard form, right? Because I have imaginary plus the real, right? So I always want it as the real plus the imaginary. All right. Now, when you're doing your operations with complex numbers, so adding, subtracting, multiplying, you're going to treat I just like a variable. You're going to combine like terms, FOIL, do whatever you need to do just as you would a regular polynomial expression. Just the only thing is if your answer includes a higher power of I, you want to simplify it fully. So for instance, if you see an I squared, you want to replace it with a negative 1. And you always want to write your answer in standard form. All right, so let's simplify some of these. All right, so something like this, 3 minus 4i plus 7 plus 6i. All we have to do is combine real plus the real. In this case, our real parts are going to be a 3 and a 7, which is going to get you a 10. And then do imaginary plus the imaginary. So negative 4i plus 6i is going to get you a 2i. And then this is our complex number in standard form. I have my real, which is 10, plus my imaginary, which is 2i. All right, I can do the exact same thing with the next one. Real plus the real, 2 plus 4 is 6. Imaginary plus the imaginary, negative 7i minus 5i is negative 12i. Just like you would a regular polynomial expression, right? This should be super easy. All right, maybe you have more things, right? Keep in mind this negative would just change the sign of everything on the inside over here. This plus doesn't do anything to the signs on the inside over here, so I get 4 plus 16 plus 5i minus 5 minus 2i. All right, and then combine like terms over here, and this is going to get you 4 plus 16 is 20, and 20 minus 5 is 15, and then I get a 5i minus 2i, which is plus 3i. And then this is my complex number in standard form. All right, now when you're multiplying complex numbers, again, just like you would if it was a polynomial, if it was 2 minus x times 4 plus 3x, you would just FOIL it, right? Same exact thing here. I can do 2 times 4, which is 8. 2 times 3i, which is 6i, negative I times 4, which is a negative 4i, and then a negative I times a 3i, which is a negative 3i squared, right? If it was an x times a 3x, it would be a 3x squared. Same thing with i's, all right? And then we can combine as much as we can. I get an 8 plus 6i minus 4i is 2i, so I get 8 plus 2i. Keep in mind, I squared is negative 1. So this is the same as minus 3 times negative 1, right? And minus 3 times negative 1 is a positive 3. So I get 8 plus 2i plus 3. And so we get two real numbers now, right? 8 plus 3 is 11. So I get as my answer over here, 11 plus 2i as my final answer. All right? So we can try the same thing over here. Keep in mind, this square cannot distribute to each of these two terms, right? Hopefully we remember this, right? Here instead, I would have to write it twice and FOIL it, right? So it's going to be a 3 plus 2i and another 3 plus 2i, and you would FOIL again as normal, right? 3 times 3 is 9. 3 times 2i is 6i. 2i times 3 is another 6i. And then a 2i times 2i is a 4i squared. But again, I squared is -1. So this I can immediately replace with a -1. And then I get a 4 times -1 is a -4. All right, so combining like terms and taking that fact into account, this is going to get us a 9 plus 12i. And then 4 times -1 is a -4. And then here you can combine like terms. So this is going to get us 9 minus 4 is 5 plus 12i as our complex number in standard form. All right. And I can try the same thing with this very last one here. All right, so 3 plus 2i times 3 minus 2i, I can just FOIL, right? 3 times 3 is 9. 3 times -2i is a -6i. 2i times 3 is a positive 6i. And then 2i times -2i is a -4i squared. And then again, I squared, I can cross that out and replace it with a -1. And -4 times -1 is a positive 4. So this is going to get us a 9. Right, -6i plus 6i are going to cancel out. Plus 4, which is 13. Right, plus 4 came from, again, -4 times -1. All right, now this is an interesting example because you see that we multiplied two complex numbers and we got just a real number, right, a real whole number. All right, this is especially important because we kind of did something similar to this way back when we were doing operations with radicals. Right, if you remember, maybe I had something like 3 plus the square root of 2 and 3 minus the square root of 2, and then when you FOILed this out, you maybe got something like 9 minus 2, which is 7, right? How did I do that so fast? There's a little shortcut to it, which I'll explain in the next slide. All right, so if you remember, right, that opposite expression had a name, and it was the conjugate, right? When it comes to complex numbers, if your complex number is written as a plus bi, its complex conjugate is defined as a minus bi, right? And when you're multiplying by the complex conjugate, you can use the shortcut a squared plus b squared, all right? And this is different from our other special products, right? If you remember from way back, our special product gave us an a squared minus b squared, all right? But this becomes a plus because remember, when you're doing this, we do an I times an I, which is an I squared, which changes that negative in the middle. All right, so let's do some examples of just multiplying by the complex conjugate. All right, so 3 plus 4i is my complex number. So my complex conjugate would be 3 minus 4i. All right, and you can FOIL this. I'll do it this time, but then the next one I'll just use the shortcut. And then I'm going to get a 9 minus 12i plus 12i minus 16i squared. And then our imaginary numbers cancel out. Remember that this I squared is going to turn into a -1. And so I get a -1 times -16, which is a positive 16. So I get 9 plus 16, which is 25. All right. Now for this next one, I'm going to do the shortcut. All right, so 5 minus 2i is my complex number. My complex conjugate is going to be 5 plus 2i. All right, and just doing my shortcut, a is my real number, and b is the number in front of the imaginary. Remember, it's a plus bi. All right, so then I get 5 squared plus 2 squared as my shortcut, right? So a squared plus b squared, which is 25 plus 4, which is 29. So you'll see that that saved us a little bit of time. All right, and so for this next one, 1 plus I, my complex conjugate is going to be a 1 minus I. And so my a is going to be 1. My b is going to be the number in front of I. If you don't see it, you assume it's a 1. So I get a 1 squared plus 1 squared, which is 1 plus 1, which is 2. All right. Hopefully we're okay with that. All right, because that's going to help us divide complex numbers. So again, like I said, when we were simplifying higher powers of I, you can't have I in the bottom, right? Because I is the same as a radical, right? So check your denominator, right? If it is a pure imaginary number, meaning there's not a real part added or subtracted with it, you're going to multiply by I on the top and on the bottom, and you're going to replace I squared in the denominator with a -1 and simplify. If it's a complex number, you're going to multiply the top and the bottom by the complex conjugate of the bottom. And you're going to replace the denominator with a squared plus b squared, and then you're going to simplify it as needed. All right, so let's try a couple here. All right, so over here, it looks like a number 19. I don't have a complex number, I just have a pure imaginary. So the only way that I can get rid of this I is if I multiply the top and the bottom by I. All right, so I'm going to multiply the top by I and the bottom. When I multiply the top by I can distribute I to each of these terms, and then we end up with a -3i plus 5i times I is a 5i squared. All right, I'll simplify that more in a second, but on the bottom, 4i times I is going to get me a 4i squared. All right, and then now any I squareds we can replace with a -1. Again, same thing over here. I squared I can replace with a -1. And so this is going to get me a -3i plus 5 times -1 over 4 times -1. And then simplifying that is going to get me a -3i minus 5 over a -4. All right, and the directions say to write our answer in standard form. Remember, standard form is a plus bi, so I do want to separate these. And I'm going to make this into a -3i over -4 plus a -5 over -4. I want my real number first, which is going to be a -5 over -4. Crossing out those negatives is going to give me a 5 over 4. Same thing over here. Crossing out these negatives is going to give me a positive. And I'm going to have my imaginary number second. All right, so this is my answer in standard form. All right, I'll do the same thing with the next one. Well, actually, I'm not going to do the same thing because the next one has a complex number in the bottom, right? It's no longer just a pure imaginary. So again, I want to multiply by the complex conjugate, and this is going to become a 1 minus I on the top and on the bottom. All right, and on the top, I can distribute that 4, and I get a 4 minus 4i. On the bottom, I can use my shortcut. A is 1 and B is also 1. So I get a 1 squared plus 1 squared, right? And then 1 plus 1 is going to get me a 2. So I get a 4 minus 4i over 2. But once again, I want it in standard form, so I'm going to split this up. It's going to be a 4 over 2 minus 4i over 2. And then these can simplify into 2 minus 2i. All right. And doing the same thing with the next one, right? Our denominator here is 1 plus I, right? To get rid of that I on the bottom, I can multiply the top and the bottom by the complex conjugate. And on the bottom, we did this in the previous example. I already know that that's going to be 2, all right? But on the top, I do want to FOIL this, right? 1 times 1 is 1. 1 times -I is -I. -I times 1 is a -I again. And the -I times -I is a positive I squared. All right, and then so simplifying that a little bit more, that's going to get me a 1 minus 2i. And then I squared is -1, so minus 1. And then 1 minus 1 goes away, and I still have 2 on the bottom. So this is just going to leave me with a -2i over 2. Our 2's cancel out, so I just get a -I as my answer. All right. And the rest of these examples are going to be very similar, right? So it's just going to be multiplying by the complex conjugate. Let's try the same thing with 22. All right, so number 22, I have a 4 minus 2i on the bottom. I'm going to multiply by 4 plus 2i to get rid of that I on the bottom. So I'm going to multiply the top and the bottom by 4 plus 2i. It looks like on the top I can FOIL. And so 2 times 4 is going to get you an 8. 2 times 2i is going to get me a 4i. 3i times 4 is going to get me a 12i, and then 3i times 2i is going to get me a 6i squared. And then on the bottom, I can use my shortcut. A squared plus b squared is going to get me a 4 squared plus 2 squared. All right. On the top, I can combine like terms, and then keep in mind I squared is -1. So that's going to turn this entire thing into -6, right? 6 times -1 is -6. And then so doing 8 minus 6 is going to get me a 2.
plus 4i times, or plus 12i is going to get me a 16i. And on the bottom, 4 squared is 16, 2 squared is 4, so I get a 16 plus 4, which is 20. And then again, I can split this up to make it a complex number in standard form, right? So I get 2 over 20 plus 16 over 20i, all right? And then 2 over 20 is going to become 1 over 10, plus 16 over 20 is going to get me a 4 over 5i. And so this is my complex number in standard form. All right, doing the exact same thing with the next one. I can multiply by the complex conjugate. Complex conjugate again. So it's going to be a 5 plus I on the top and on the bottom. All right, and on the top I can FOIL once again. So this is going to get me a 15 plus 3i plus 10i. Hang on, let me make sure that's clear, right? That's a 3. All right, so I get 3i plus 10i plus 2i squared. And on the bottom, I can use my shortcut again. All right, so a squared plus b squared is going to get me a 5 squared plus 1 squared. And this is going to get me, right, 2i squared is the same as negative 2. All right, so 15 minus 2 is 13, plus 3i plus 10i is 13i. And on the bottom, I have 5 squared is 25, 1 squared is 1. So 25 plus 1 is 26. And then you can split these up, so I get a 13 over 26 plus 13 over 26i. And then these do simplify, right? It becomes 1/2 plus 1/2i. All right. One more just like that. All right, so I can multiply the top and the bottom by the conjugate. And it looks like the conjugate here is going to be 4 minus 3i. All right, it's just the conjugate of the bottom. And then on the bottom, we're going to have our shortcut 4 squared plus 3 squared. And then on the top, I can FOIL, right? 4 times 4 is 16. 4 times negative 3i is negative 12i. Negative 3i times 4 is negative 12i. And then negative 3i times negative 3i is a positive 9i squared. All right, and then 9i squared, I'm going to cross that out and change it to its opposite. It's going to become a negative 9. All right, and then 16 minus 9 is going to get you 7. And then negative 12i minus 12i is negative 24i. Over 4 squared is 16, plus 3 squared is 9, and 16 plus 9 is 25. All right, and then so, again, I can split this up into 2, and I'm going to make this 7 over 25. All right, minus 24 over 25i. All right. So some of them might be a little bit tedious, right? And again, we do want it in standard form, so a plus bi, all right? But the more you do them, the easier they should get, all right? Same process every time and same patterns every time, all right? So that's your introduction to imaginary numbers and complex numbers. In our next lesson, we'll actually apply these into solving some equations.